Today's lesson is on chapter 3.4 and 3.5 in the textbook. Before we begin, let's recall what we learned last lesson. We learned about exponent laws, which are a way for us to simplify expressions involving powers with the same base. Here's an example. Let's simplify this algebraic expression by applying the appropriate exponent laws. So remember to simplify the numerator and the denominator separately before simplifying together. Beginning with my numerator, I'm going to simplify my coefficients 4 and 2 together. 4 times 2 is 8. Then I'm going to simplify my a factors together by keeping the base the same and adding my exponents. Then I'm going to simplify my b factors together, remembering that this b has an invisible exponent 1. So the base will be b, and 5 plus 1 is 6. And I'm going to simplify my coefficients together, 8 and invisible coefficient 1. 8 times 1 is 8. My a factors will be simplified together. So this a has an invisible exponent 1. 1 plus 2 is 3. And then simplifying my b factors together. 2 plus 4 is 6. Now I can simplify my numerator and denominator together. My coefficients will cancel each other out. 8 divided by 8 is 1, and I don't need to write the coefficient when it's a 1. What will also cancel each other out are the b factors. So what I'm left with is just my a factors. So remember, this is division, so I'm going to subtract my exponents. Base a, exponent 5. Let's move on to today's lesson. In 3.4, we're going to learn all about polynomials. So we have the expression 4x squared. We call this a term. A term consists of two parts: the coefficient and the variable. Sometimes the variable may have an exponent that's greater than 1, but it may not always. In this example, we have an exponent 2. So we've labeled it as the exponent. The variable is the base. In this example, the variable is x, and the coefficient is the numerical value in front of the variable. And in this example, it's 4. In example 1, it's asking us to identify the coefficient and the variable of each term. So we have the term expressed to us in words and then algebraically. In words, part A says, Jim earns $7 per hour at his part-time job. If he works for X hours, his earnings in dollars are 7x. In algebraic form, the algebraic expression would be 7x. The coefficient of 7x is 7, and the variable is x. B. The depth in meters of a falling stone in a well after 2 seconds is negative 4.9 t squared. The expression form of this is negative 4.9 t squared. and the coefficient is negative 4.9, and the variable is t. The table continues on the next page. C, the area of a triangle with base b and height h is 1 over 2 base times height. The coefficient is 1 over 2, and there are two variables, b and h. D, the area of a square with side length k is k squared. The expression is k squared. The coefficient, there's an invisible 1 in front of the k squared. And we know that when the coefficient is 1, we don't include it. And the variable is k. Amir walks 6 blocks to school. The expression is 6. The coefficient is 6, and there are no variables. A few things to note. When there is no visible coefficient in front of the variable, we understand that the coefficient has a value of 1. When there is no variable part in a term, we refer to the term as a constant term. So just like part E, there wasn't a variable part of the term. So the coefficient alone, without a variable attached to it, we call it a constant. When you're asked to state the variable of a term, the exponent is not part of the variable. Okay, and just like in D, k squared was the expression. We did not include the exponent 2 with our variable. A polynomial can be classified by the number of terms it has. A monomial has 1 term. And there's some examples there showing you that those are individual terms and they're all individually called a monomial. A binomial means 2. There are some examples there that show you that each expression contains 2 terms. We call them binomials. And a trinomial has 3 terms. And again, there are 2 examples there showing you what 3 terms look like. An easy way to distinguish the start and the beginning of a term are the adding and subtracting signs. They break up the terms. So 2x squared is 1 term. Following that term, we have an addition operation, and that addition operation also serves as a positive sign for the next term. And then we have the constant term of -1 at the end. So those are 3 terms inside this trinomial. For polynomials with more than 3 terms, you can classify them as fill in the blank with the number of terms. For example, a plus b plus c plus d plus e is a 5-term polynomial. It has 5 terms in it, so we just call it a numerical value 5-term polynomial. All right, so let's classify the following polynomials by name. Part A, the polynomial has 2 terms. 1, 2. So we call this a binomial. Next, we have 1 term. This is called a monomial. Continuing on the next page, we have 1, 2, 3 terms. We call this a trinomial. And finally, this is 1 term. This is 2, 3, 4. So we call this a 4-term polynomial. Let's practice with a word problem. Cheryl works part-time as a ski instructor. She earns $125 for the season, plus $20 for each children's lesson, and $30 for each adult lesson she gives. Write an expression that describes Cheryl's total earnings for the season. Identify the variable and the coefficient of each term, and explain what they mean. So she earns $125 for the season. That doesn't change. No matter how many lessons she teaches, she's always going to get $125. It also says that she earns $20 a lesson for kids and $30 a lesson for adults. So writing this as an expression, 20C plus 30A plus 125. Variable C represents the number of child lessons Cheryl teaches in one season. We're going to multiply that number by 20 because she's getting paid $20 per lesson. Variable A represents the number of lessons she gives to adults in one season. We multiply that by 30 because that's how much she charges for one adult lesson. So 30A, we read it as 30A, but we understand that that means 30 times A. Same with 20C. We understand that that means 20 times C. And finally, plus 125. We're not going to multiply that by any variable because it's a fixed cost. It doesn't vary according to how many lessons she teaches. She could not teach a single person in a season and she still gets $125. All right, let's complete the chart with each individual term in the polynomial, starting with 20C. So the C represents the number of child lessons, and the coefficient 20 represents the cost for one child lesson. Next term, 30A. The variable A represents the number of adult lessons. And the coefficient, 30, represents the earnings for one adult lesson. Finally, we have our constant term. There is no variable in this term. The constant represents the fixed earnings per season. B. One winter, Cheryl gave 8 children's lessons and 6 adult lessons. What were her total earnings? So 8 child lessons and 6 adult lessons. So in our expression that we created in part A, I'm going to write that down. I'm going to substitute 8 for variable C. And I'm going to substitute 6 for variable A. At the bottom of this page, there are some homework questions for chapter 3.4. I encourage you to stop the recording now and complete these questions before continuing watching lesson 3.5. Chapter 3.5, collecting like terms. Like terms are terms that have the exact same variables and exponents. So examples of like terms are 2x and 7x. They both contain variable x. And 3x squared y and 5x squared y are also like terms. They both contain the terms x squared y. This is the variables in the term. So all the variables and exponents within that term have to match each other for them to be like. What's not the same is x and x squared. Those are not like terms. Although they both contain base x, their exponents are different. Remember that this x has an invisible exponent 1. So the exponents need to match, and so do the variables. And 3x squared y and 15xy squared are not the same. Although they contain x, y, and exponent 2, they're not in the same order. So they're not like. The exponent 2 is part of the x factor in this term, whereas the exponent 2 is part of the y factor in this term. Let's practice identifying like terms. In A, we have a bunch of terms here. So the like terms are 2x, 8x, 3x, 3x. 2 is not included as a like term because it's a constant. It doesn't contain variable x. Next, the like terms here are 4a squared and a squared. All the other terms either have a different exponent value or an additional variable or a completely different variable. In part C, 3u squared is like with 2u squared. Additionally, we have two constants that are like. To simplify a polynomial expression, add or subtract like terms by adding the coefficients and keeping the variable the same. To simplify an expression is to find an equivalent, simpler, and shorter expression. Let's practice adding like terms. So 4x and 3x are like. They both contain the variable x. So adding them, I'm going to just keep the variable the same and add the coefficients. B. 4x plus 3 plus 2x plus 5. Not all of these terms are like. So what I'm going to do is I'm going to reorder the order of how this expression is presented to us. I'm going to keep my like terms beside each other. We call this collecting like terms. When we collect like terms, we ensure that we don't miss adding or subtracting any like terms together that are somewhere else in the expression or the equation. So they're beside each other and it's easier for us to read and less likely for us to make a mistake or forget a term. In my next line, I'm going to only simplify like terms, which means I'm only going to add together the terms that are like. So 4x and 2x can be added together. Which equals to 6x. And then 3 plus 5 can be added together, which is equal to 8. Let's practice subtracting like terms. 8x subtract 3x is equal to 5x. 5x squared subtract 2x subtract 3x squared subtract 9x. So I'm going to collect like terms. When you are moving a term in an expression, remember to also move the sign or operation that's right in front of the term because that sign belongs to the term. So I move the negative 3x squared term to be closer to its like term, 5x squared. So I moved this negative with it to here because that negative belongs to the coefficient. The coefficient is negative 3. So that negative had to move with the term. And then finally, I can simplify my like terms. 5x squared minus 3x squared is equal to 2x squared. Negative 2x minus 9x is negative 11x. Adding and subtracting to simplify algebraic expressions is called collecting like terms, which I already introduced you to that. Here in the gray box is a summary of how to collect like terms. So group like terms together, add or subtract the like terms only. You're going to apply integer rules to the coefficients of like terms and do not change any of the variable parts. So we already practiced collecting and simplifying like terms in the previous page, but we're going to continue to practice on this page. So first, I'm going to collect like terms. And then I'm going to simplify my like terms. In B, I don't need to collect like terms because my B terms are already together and my constants are already together. So all I need to do is simplify. 2b subtract b is b, and 7 minus 8 is negative 1. C, I'm going to collect like terms. And then I'm going to simplify my like terms. Positive 3r squared subtract 3r squared, they're going to cancel each other out. So I don't need to include them in my final simplified expression. Negative 6r plus 9r is equal to 3r plus 2. And finally, I'm beginning with collecting like terms. And then simplifying like terms. Something to note is the order of how we write our terms. Our constants are always going to be last. Notice that in this question, I always wrote the constants last. We begin by writing the term with the highest exponent. So in part C, we wrote our r squared terms first, and then our r terms next. Remember, these r terms have an invisible exponent 1, and then following with our constant. Your answer should be presented with the highest exponent term first and ending with your constants. Example 5. A rectangular field has a length that is 8 times its width. Draw a labeled diagram of the field. Let W represent the width of the field. I'm going to start off by drawing my field. And it tells us to label our width with variable W. Okay. And we know that the length is 8 times the width. So instead of labeling my length with L, I'm given the information that it's 8 times the width. So whatever the width is, I know that my length is going to be 8 times it. B, write an expression for the perimeter of the field. So perimeter equals to length plus width plus width. Instead of using L, we're using 8W for the length instead. But perimeter is still adding up all of the sides and simplifying that to 18W. Find the perimeter of the field if it is 500 meters wide. So I'm going to begin with my formula for perimeter, and I'm going to input my value for W. And then solve. So it was important for us to substitute length L for 8W in order for us to find the value of perimeter. There are some homework questions for chapter 3.5 here at the bottom. Please complete these and then complete today's quiz. If you have any questions, you may join today's Zoom, message me, or email me.